Okay, so we'll show you the solutions to the January 2017 Common Core Geometry Regents exam. All right, so for number one, pretty nice here. They give us a line to be parallel to. Keywords parallel. So with parallel and perpendicular, let's not confuse those. Parallel, we need a line with the same slope. That's how we're going to produce parallel. So what is the slope of this line? It is the number that's being multiplied by x, 1/2. All right, so that means you're going to go up 1, right 2, you know, that type of thing. So then what we need to do is go through this point. Now we can do this algebraically, point slope form, slope intercept form, or we can graph it. Now in a case like this, it's easy to graph. So let's do that. Negative 2, 2 is that point. From there, we're going to go up 1, right 2. Of course, you can go down 1, left 2 to keep the pattern going, whichever way you got to go. Now, as far as the y-intercept goes, that's your b, that's 3, right? In this format, m's your slope, b's your y-intercept. So we've got it. That's our best choice right there. These other two, no good because the slopes are wrong. This one's no good because the y-intercept's wrong. Number 2. Okay. All right, dilation and reflection. Okay, so basically what we're looking at here is we have similar figures. Okay, so triangle ADE is going to be similar to triangle ABC. Now, if you look at your choices down here, okay, it's all to do with angles. Okay, so its corresponding angles are congruent is what they're looking for. Because you have similar figures. All right, the dilation is suggesting we have similar, not congruent. Okay. All right. Now, the half with angles would only be around if there was a bisector. We don't have that guarantee, so let's get rid of those. What we do have is congruent, corresponding angles. Now, these are congruent. Let's check them out if they're corresponding. So follow the path B to A to C, you're talking about that angle. A to E to D, you're talking about that angle. Angle A, this one's not corresponding to angle E in that one. So that's not it. All right, let's get rid of those markings for a second. And let's check this out. A to B to C, follow that path, that's this angle. A to D to E is this angle. All right, those are corresponding. That has to be true. All right. Which one's not always true? Okay, we're given a congruence statement. That's what this is. A congruence statement. And from there, we know corresponding parts of congruent triangles are congruent. All right. Which one's not always true? Okay. A is corresponding with D, so that one is true. Areas are the same. That has to be true. Perimeters have to be the same. Maybe it's this one. BC is... Okay, BC is not corresponding to DF. If you look, those are the second and third letters in our statement. D and F are the first and third letters. They're not corresponding. All right. Next one is kind of tricky here. All right. You're looking at... All right, we want to do something with this figure in here. Okay. Let's see, these two are the same. This one's mid-segments. Here we go. Let's talk about this. So basically what happens is D, E, and F are all midpoints to their side. So these are the same over to there. Let me just get rid of this star here. So if you check it out, this is the same as that. Okay. We actually don't need that one. Let's get rid of it. Let's try another pair. Because I see where they're trying to go with this. All right. So basically, this whole thing right there, AB, is essentially going to be equivalent to these two added together. So AB is going to be the same as AD plus EF. Okay, if you can see that. So mid segments are half as big and parallel to the side. They don't touch. That's why EF is the same as half of AB. All right, same thing's going on over here. Look at AC. Okay, these two are the same as each other, and it's the same as that. So these two, right, are going to add up to AC. So AC is going to be the same as DE plus AF. Now, if we take the perimeter of this whole thing, that's all four of those added together. So that's going to be the same as these two added together. Wow, that's pretty tricky. Right? This is all the perimeter of ADEF. And that's what it's equivalent to. Kind of tricky, but that one works out well. So that's the mid segments and a little twist on how to get you to be tricked by that. All right, next one. Not easy. All right, this triangle right here is given to be congruent to this triangle. Okay, so we're told that. All right, we don't know if these angles are right angles. They look it, so a lot of people maybe just fall for that. We cannot be sure. We do know these are congruent, but we don't know if they're right angles or not. Okay, we do know that these are the same, right? Now, what you look for, here we go. When you see a backwards N or Z or N, these angles in the corners, right, inside corners, if they're congruent, those sides are parallel. Alternate interior angles theorem. It's kind of the converse of it, right? It's backwards. Okay, so that forces these sides to be parallel. That's good. The other key piece. So AB is congruent to CD as well. There we go. So this side is not only parallel, but it's also congruent because of the congruent triangle. So these are the congruent. This figure must be a parallelogram at least. Okay. So it could be these other ones. Let's see. But I don't have any guarantees. So it can be proven this parallelogram. I'm not confident on any of the others. So I've just got to go with parallelogram. It's the least specific. And if they gave us something more, we could probably, step it up. But that's it. All right, not congruent. So we're looking for transformations that are not rigid motion transformations. Okay, that's what we're looking for, not rigid motion. Well, reflection is, line reflection is, so we got to throw it out. Rotation is, and translation is. The only one that may change size is dilation. Scale factor 2, it will change the size. So that's the one we want. All right, here goes on number 7. Okay, kind of a strange trig problem here. All right. Well, there's the most efficient way of doing this, but then again, you very well could get tricked by that. All right. You know what? I'm gonna go with a long direction with this, but there's a way more efficient way. if this is theta and these are similar figures, here's what they're showing. Those angles are the same. Those angles are right angles, so they're the same. You can essentially tell that this is theta right here. Now, if we knew what theta was, we could solve for x, right? We could. So one way is to go find theta. All right, so tan of theta equals 3 over 7. And how do we get theta? Well, let's first change 3/7 to a decimal. And that gives me, looks like, yeah, 0.4285. Okay. Now, to get theta, we have to go tangent inverse. We want to get rid of tan. Can't divide by it. We have to perform the inverse operation. So tan inverse of tan is going to, those two are going to knock each other out here in a minute. Whatever I do to one side, I got to do the other. So tan inverse of tan brings out theta. And it looks like in degrees, this is 23.1986. Okay, now that just gets us the angle. Kind of weird after you see what's going to happen. So now we're going to go back over here. Now we know that this is about 23 degrees. We're going to go tangent of 23.19. All that is equal to opposite over adjacent. Okay, so what is that? Tangent of that is strange. If you take tangent of this, you go right back to 42857. Put it over 1. Opposite is 2.4. Adjacent is x. Right? We label that. Okay. When we cross multiply and divide, you get approximately what? .6. Yeah, close enough. Now, there was a much more efficient way of doing that. Okay. If I would have put 3 there, 7 there, we could have set up proportions, which would have been much more efficient. You know, 3 is to 7 as, let's go 2.4 is to x. You'd have gotten the same answer. So a lot more efficient, but, you know, just trying to figure out, probably most of my students are going to go through that. All right, get a little more room here. Okay, this problem is a little strange. More of a pre-calc, you know, optimization problem, but all right, biggest area. So you've got 64 feet of fence. So the perimeter here, let's say we have a length and a width, right? We've got 64 feet of fence to work with. Okay. So actually, you know what? Let's just call this, let's try it again. Let's call the length x. Then that would make this x. And this would have to be 32 minus x, right? Yeah, because if you add all these up right now, that perimeter, x plus 32 minus x plus 32 minus x, that's all 64. So algebraically, that's how you'd have to do it if you're going to do this algebraically. Okay. Yeah, this could get messy. Let's not do this the pre-calc way, even though we could. Let's just guess and check. If the length and width are equal, and you get 64 feet of fence to work with, that's 16 each. Now that's going to produce an area of 256. All right. Yeah, this is probably the way to go. Just guess and check. If there was an open response and we needed an algebraic solution, we'd have to use this, but we don't know pre-calc yet, so let's just guess and check. Now what do they mean here? The length is 2 more than the width. Okay, so if I bring, let's say bring this down to 15, then that makes that 17. That is a length of 2 more than the width. Now let's convert that. The area for that one is at 255. Okay, let's do it again. 4 more than the width. Let's bring this down to 14 and make that 18. What you have to do is make sure when you add these up, I forgot to mention this, adding them up, you got to make sure that the perimeter is 64 to hold that 64 feet of fence, right? Now for area, you just want length times width. And 18 times 14, that's 252. Looks like your best area, your highest area is going to be when the length and width are the same. But just to be thorough, let's fully work this problem here. Let's go over to the third case, 6 more. Let's take this down to 13. That would be 19. Yeah, that adds up. If you had 13 and 19 in these spots, you get 32 for the perimeter. And then for area, what's 13 times 19? 247. Okay, so this is your best one. Length and width are equal. All right. Looks like a trig problem. We need the perimeter of the rectangle. Oh, it's not a trig problem. It's a special right triangles problem. We should know with a 30, 60, 90. You get a ratio of 1 to 2 to square root of 3. We should know that. We should have it memorized. But in case you don't, we can just use some trig. So if you already know this, it's probably you're not needing help on this anyway. So let me just do it the trig way. Let's go with opposite and hypotenuse and adjacent. All right. So first, we'll get x, so we'll call that y. Let's get x first. Let's see, we need the hypotenuse involved, so probably sine 30 equals opposite over hypotenuse. Sine of 30 is 0.5, put it over 1, and cross multiply. 0.5 times 12 is 6. All right, now you see that 1 to 2 ratio idea that we had over here. All right, now for y, let's go cos of 30 is y over 12. I believe that's 8660. Just double check that. Yeah, we got that. All right, that's good. So now y equals whatever 0.8660 times 12 is. So that is, let's see, 10.39. Now, what we got to be careful on this problem, yeah. We got to make sure that we understand that there's 2 of those. Another 10.39. What's after it? Yeah. So we've got perimeter is going to be 2 of those 6s, 2 of those 10.39s. I get the closest perimeter I get is 32.8. Okay. And there we go. A couple more for this video session. Yeah. All right. What I like to do with this is, okay, doesn't look like it changed any size, but I really wish, yeah, sequence of transformation, so that's could be more than one step. Oh, okay, let's go orientation. The best bet is orientation. Start with that. The size looks good. Now we'll talk orientation. What I mean by that is, if you follow A to B to C to D, you have an arrangement of the letters that is clockwise. Let's go in clockwise. Now, A to B to C, D is going in a counterclockwise direction, or the image, I should say, double prime. Now, what does that do for us? Well, that tells us that we need an odd number of line reflections involved, okay? Even number would get us the same orientation, a rotation, a translation. Any of those things are just going to, they're just going to continue to give us the same orientation. So we need an odd number of line reflections, 1 or 3 or more, just as long as it's odd. Now, looking at this does not have a line reflection. Dilations preserve orientation. This is not preserved. So a dilation and a rotation can't possibly be. Translation rotation preserves orientation. You don't have that odd number of line reflections. Okay, here we go. That's 2 line reflections. That will put the orientation back. So it's a single line reflection. Then we can translate. Don't need specifics. We just needed orientation to fix that problem. All right. Great. This is a volume question. We've got, okay, so we've got to get a volume of the prism. That's base times height, but the B is capital B. Okay, it's really length times width times height. So it's got a 4. Let's see. Sides of 4 by 4 by 6. All right. So that's going to be what, 96 it looks like. Let's double check that here. Yeah. Okay. So then what we have is the volume of the cylinder that we're going to cut out of it. Okay, the radius is 1, and it's a full cylinder, not a cone. So you're going to have pi r squared h. All right, the radius is 1. The height is still 6. So the volume of the cylinder looks like it's going to be approximately 18.849. And we're just going to subtract those. You're looking at approximately 77.15. So there you go. Last one for this session. Looks like a straightforward trig problem. All right. Find the value of x. There's foot. This is in feet. Label the diagram opposite, adjacent, hypotenuse. Go ahead and write your acronym. To help you remember your trig functions. To me, it looks like adjacent and hypotenuse are involved, so let's pick cosine. So cosine of 40 degrees equals adjacent over hypotenuse. Now, cos of 40, just quick type that in your calculator. Let me do that right now. And we get 0.7660. And I try to teach my students that it's a ratio of 2 sides, right? Adjacent to hypotenuse. So let's put it as a ratio. Now we can get the cross products, right? Cross multiply. And we'll divide. Don't be surprised here. We're dividing by a number less than 1. The number will get bigger. Okay? So this one's out. It comes out, just let me type that in. Yeah, 18.27 is what I'm coming up with. Yeah, closest one is 18. All right, that's it for this session, and we'll pick up the next ones in a minute.